So the last topic we need to cover is some two-dimensional collisions here in momentum. And it's still conservation of momentum, but remember that momentum is a vector. So the vector can be in 2 dimensions. So what we want to do is we want to split the momentum into the horizontal and vertical components if the momentum is sort of like being conserved in multiple directions. Okay, now you do want to think about the conservation separately in each direction. That means there could be a vertical impulse, there could be a horizontal impulse, and it may be conserved in one sense. If there's no horizontal impulse, for example, it may be conserved horizontally, or it may be conserved vertically if there's no vertical impulse, or it may be just, conserved in both directions or neither direction, right? It depends on the scenario, but the way we handle 2D stuff, just like we do with kinematics, just like we do with forces, is we decompose everything into their horizontal and vertical components and then handle them separately. So the general strategy is conservation of momentum in the horizontal direction and conservation of momentum in the vertical direction if it applies. Okay? And so that's the basic idea of what we're going to be doing here. Is that we just want to make sure we can apply it, and we want to think, hey, should momentum be conserved in this direction? If so, we'll apply conservation of momentum. Okay, so let's kind of like take a look at some examples, really. Just kind of illustrate that a little bit. So I have a billiard ball labeled 1, moving horizontally, strikes another billiard ball labeled 2 at rest. Okay, so they're moving like this. Before the impact, this guy was moving at 3 meters per second. Let's move this closer so I can kind of show you what happens afterwards. And this guy's moving at 0. And after impact, it is moving at 0.5 meters per second at 50 degrees from the original direction. So now this guy, we'll call this 1, we'll call this 2. 1 is now moving 50 meters per second at an angle of 50 degrees. Okay. From the original direction. If the 2 balls have equal masses, what is the velocity of the ball 2 after? So ball 2, what is ball 2 going to be doing? Probably going somewhere like this way in some unknown velocity. Okay. So this is what I want to figure out. I want to know this guy's velocity. Well, let's look at the momentum horizontally and vertically in this case. Because what's happening initially in the horizontal direction, and remember, we still got to say direction. So let's say right is positive. In this case, we're going to say up is positive for the vertical direction, just like we do in kinematics or, with our net forces. We always establish directions. So in the x direction, the initial momentum is just m times 3 plus m times 0, right? Because this guy's moving with speed 0. So it's m times v of this guy plus m times v of that guy. That is just 3m. We're going to assume they're the same mass. They're both billiard balls. Those are pool balls, so those are kind of like the same size. And then in the y direction, no object has any vertical component of velocity, so they don't have any momentum in the vertical direction. Okay, what about this guy? Horizontal direction. Well, I have to decompose things into their horizontal and vertical direction. So I'm going to call this, let's say, we'll just call this is 50 cosine 50 degrees, right? Just like we decompose. And then the vertical component here is 50 sine 50 degrees. Then this guy, I don't know. I'm just going to call it Vx and Vy, right? Because I don't know either of those anyway. Okay? So what is the total momentum in the x direction? Is this m times his velocity in the x direction, which is 50 cosine 50 degrees, plus m times Vx. That's the horizontal momentum velocity of this guy. Okay? And then in the y direction, so from conservation of momentum, this quantity has to equal 3m, right? Conservation of momentum. The x component of the momentum should equal the x component. How about in the y direction? We said up was positive, so the final momentum in the y direction is m times this vertical component, which is positive, 50 sine 50 degrees. And then plus m, but his velocity is downward, so let's make it negative Vy. And that momentum has to add to 0, right, by conservation of momentum. So both equations, I can divide out the m, right? And then this one, I can solve for Vx. It is 3 minus 50 cosine 50 degrees. Okay, so that is... Oh, I don't know why I said 50. It's 0.5. So these should be 0.5 here. My bad on that. I was going to say, that's like, look, a really small... that was a really big number if it was going at 3. 3 minus 0.5 cosine of 50 is 2.67 meters per second. So that's the horizontal velocity. And here, Vy is just going to be 0.5 sine 50 degrees. And that's 0.38 meters per second. So now, this is what I know from this picture. I know the x component of the velocity is 2.67. I know the y component is downward at 0.38. And I want to know what a couple things, what the angle is and the hypotenuse. So the speed is going to be the square root of 2.67 squared plus 0.38 squared. And I get about 2.71 meters per second. And then the angle, because they want to know the velocity, so the direction, you would just say tangent inverse of y over the x value, right? The opposite side over the adjacent side. And I get about 8.1 degrees. Okay, so he's moving down and to the right at 8.1 degrees with a speed of 2.71 meters per second. Okay, so it's pretty much the same process. It's just you have to decompose into the horizontal and vertical components when we're doing this. Okay, so here we have a family skating. The father skates at 8.2 meters per second, collides and sticks to the mother, who is initially moving at 3.3 meters per second and 45 degrees with respect to the father's velocity. The pair then collide with their daughter, 30 kilograms, who is stationary, and the three slide off together. Okay, so let's say the daughter's here. We'll say the father's here. Oops. The father is 75 kilograms and moving at 8.2 meters per second. And then we'll say I don't know, it just depends on the direction you want to say, but let's say the mother who was moving 45, let's say the mother was going this way at 3.3 meters per second, and that angle is 45 degrees, okay? And then they all collide together, and then they move off, okay? So now we have three objects in our system. So let's look at the x. Let's look at the initial momentum. I'm going to do it this way. I'm going to do x and y. The initial momentum, well, I need to decompose the mother into the x and y components, right? So this is 3.3 cosine 45 degrees. And this side is 3.3 sine 45 degrees in terms of velocity. So then I just add up all the momentums of all three of them, each one of them one at a time, right? So it's 75 times 8.2. Then the mother's momentum, what was the mother's mass? The mother was 50 kilograms. And the daughter was 30 kilograms. Okay, so then 50 times 3.3 cosine 45 degrees. And then we don't include the daughter because the daughter doesn't have any momentum at all. So the initial momentum is 7.5 times 8.2. Oops, let me use this calculator. 7.5 times 8.2 plus 50 times 3.3 cosine of 45 degrees. Oops. And I get 731.7. Okay, kilogram meters per second. Okay, and what's the final momentum is just equal to that. It's all three of them with the same mass, so 75 plus 50 plus 30 moving at some Vx direction, right? And so we're going to set that equal to 731.7. Now, how about the y direction? The initial momentum in the vertical direction. Well, the father doesn't have any vertical velocity. Velocity is only horizontal. But the mother has some component vertical. So we'll say up is positive. So just to be clear. So then we're going to say it's 50 times 3.3 sine 45 degrees. Oh, I think I messed up on the calculation. It's not. I didn't do 3.3. Oh, so this should have been, oops, 626.7. 626.7, okay? And so here is so the mother doesn't have any vertical momentum, and the daughter doesn't have any vertical momentum, and the father doesn't have any vertical momentum. So the mother just has this vertical momentum. And so that equals the final momentum is just, again, the total mass of them times the Vy direction, right? So then we're just going to solve this equation. Vx is this divided by 155. So that's 4.04 meters per second. And then V sub y is going to be 50 times 3.3 sine 45. Divide that by, what did I say, 155 kilograms. And so the Vy is going to be 0.75 meters per second. So their final velocity is square root of the x component squared plus the y component squared, right? Because it's going to be has a rightward component and an upward component. So we do the hypotenuse to find the magnitude there, right? This final velocity. So square root of 0.75 squared plus 4.04 squared gets me about 4.1 meters per second. So that's how fast they're going, and you can use tangent of the angle if you want to find the angle. Now, what was the change in the kinetic energy? Well, so with kinetic energy, remember, you always want to look at speed. So how much kinetic energy was there initially is the father had 1/2 m times his v squared. And then this person, 1/2 m times v squared. Okay, and the daughter didn't have any kinetic energy. So just add that up. That is 2793.75 joules. And then the final kinetic energy is 1/2 their total mass. Combined mass is 155, and their speed was this 4.1 squared, right? And so I get 1309.1 joules. And so the change in the kinetic energy is just whatever the final kinetic energy is minus the initial kinetic energy. So that, subtracting that quantity, we get negative 1485 joules. So we lost energy, which is very common in a collision to lose kinetic energy like that. Okay? So try third example here. So two cars of the same mass approach an extremely icy four-way perpendicular section. Car A is traveling northwards at 30 meters per second. They have the same mass, so we just call it M. And then car B is traveling eastward, and they collide at stick together, and they travel. So I don't know his velocity. Then after the collision, they travel together north of east. North of east is here, so 28 degrees like this. They have 2m, and they move some velocity, but they don't, like, we'll just call it v2 or v final. But again, not given to us. Okay, and they want us to figure out the initial velocity of the car. We'll call this v0. Okay, so let's take a look at, again, it feels like you don't have enough information. Okay, it feels like, don't I need to know the speed or something of one of them? But let's just apply the principles, right? So in the initial direction, so in the x direction, the initial momentum is, if we include these two guys in the same system, right? The x momentum, the horizontal momentum, is just this guy, mv0. Right? Because this guy doesn't have any horizontal velocity. And in the y direction, the initial velocity, if I say up is positive and right is positive, his initial momentum is just m times 30, or 30m. Right? Because this guy doesn't have any vertical momentum. So you add up the momentums of each. Now, how about the final momentum? Well, they're both moving together, and you know it's 28 degrees, so why don't we decompose this and call this VF cosine 28 degrees, and this is VF sine 28 degrees. So the final momentum horizontally is 2m VF cosine 28 degrees. And then the final momentum in the y direction is just 2m, they're moving together. and they're moving at VF sine 28 degrees. It's their velocity in the vertical direction. And so this one has to equal mv0 by conservation of momentum. And this one has to equal 30m by conservation of momentum, right? So we do the conservation of momentum horizontally, conservation of momentum vertically, and then do that. So we can make some simplifications. The m's are going to cancel. So what I need to do is figure out what VF is so I can solve for V0, because I'm trying to figure out what the initial velocity, I'm trying to figure out this velocity right here, V0. So how am I going to solve this? I got two equations, but this one I can solve for VF. VF is equal to 30 divided by 2 sine 28 degrees, right? So I can get that number is 30 divided by 2 sine 28 degrees is 31.95 meters per second. So that's how fast they're moving finally. And then you can plug that into here. 2 times 31.95 times cosine of 28 degrees equals V0. And there you go. I get 56.4 meters per second. Okay? So don't be afraid. You know, it turns into a math problem once you set up the core like conservation of momentum equations, and it's just a math equation you got to solve. All right?